So for the next lesson 3.2, we're talking about maxima and minima. So what we're trying to find out is how do we determine the location of these points? So how can we figure out the location of the maximum point and the minimum points? So let's just go over some key terms first. So critical number we talked about in the last video. So if I had a function f of x and c is the critical number, right? So that is the number, the x value where the derivative is equal to 0. So if c is a critical number if the derivative of that number is equal to 0, or when I get the derivative at that x value, it doesn't exist. So we know at that critical number that something important is happening on the graph, but just to know it may not always be a turning point. We just know that there's something important that's happening. Most likely it is, but we can't say for sure, right? So a critical point is, again, if we had a function f of x and c is our critical number, then the critical number here would have been my x value, right? C is my x value. So the critical point is just simply turning it into a point. So if I have my x value, I'm subbing in my c, my critical number, into the function to get my y value. And therefore I just have my xy coordinate point there. That's all that's saying. That's the coordinate of the critical point where something is happening. My local extrema is also known as a local maximum or local minimum values, or again, turning points. And it's found by testing the values around the critical numbers using the first derivative test. So again, we did this in the last video where we had our critical numbers, but then in our chart, we were testing the values around the critical numbers to find out what was happening if I was having a local max or a local min. And again, we'll do that in an example today as well. So that was using the first derivative test. So what is the first derivative test? So let c be the critical number that we found, right? And again, we're just saying that we're on a continuous function here, f of x. So if the derivative changes from positive to negative at that c value, at that critical value, then the function would have a local maximum at c. So again, let's follow this through here. If the derivative is changing from positive to negative, so if I'm going from positive then down to negative, right? Then at that c value here, I would have a local maximum, right? So here my derivative is greater than 0, and here my derivative, right, is decreasing, is less than 0. Here, if I have my derivative changing from negative, it was negative, and now it's changing to positive, right? Then I would have a local minimum at that c value. At that critical point, that turning point would be a local minima, a minimum value. So again, here the derivative would be less than 0, and here my derivative would be greater than 0. And in this example, if the derivative does not change at all, it does not change signs, it's not going from positive to negative or from negative to positive, then obviously I don't have any local maximum or minimum points at c. There's no turning point there. What about an absolute extrema? Absolute. Also known as, you can call it an absolute maximum, right? Or an absolute minimum value. And so what we mean is, just to say here, it only occurs, if you remember from 12 functions, for even degree polynomials. Only for even degree polynomials. So what we're saying is, let's look at something that would be quartic from grade 12. So, just something that looks like this, let's say. So to the degree of 4 is what I'm saying. So this would be a local minimum, but the absolute minimum, right, would be the absolute lowest point along the curve. So this would be the lowest point here. And I know I said it's only for even degree polynomials, so like 4, but found at local extrema or at the endpoints of an interval. So what do I mean by endpoints is, let's say we were talking about something that was cubic. So that looked like this. it could not be a continuous function, is what we're saying. We'd have to have endpoints there. So this is cubic, but it's a closed interval. So it's closed at either end. And then I could determine what my absolute maximum or minimum are. So again, it's found at the local extrema, so here, or at endpoints of an interval is where I can get my absolute extrema. And we'll go over an example of that as well. Let's start with one. And we're reviewing some of the last lesson in here as well and continuing on from it. So example 1, for this function, cubic, 2x cubed minus 3x squared minus 12x plus 2, determine what the critical numbers are. So where are the critical numbers? The critical numbers are where, right? The derivative, what? Those critical important values are where the derivative is equal to 0. So what I should do first then is get f prime of x and get the derivative. So 6x squared, 1 less, minus 6x to the power of 1 minus 12x to the power of 0, which is now gone, and that would be plus 0. So 6x squared minus 12x, sorry, 6x squared minus 6x minus 12. And again, make that equal to 0. That is where the derivative is 0. So make the derivative equal to 0. And then to get the critical numbers, I need to solve for x. Right, so in order to solve for x, how do I do that? How have we been doing that? Is there any type of factoring I can do here? GCF first. So I can't take out an x, but I can take out a 6. So then I would be left with x squared minus 1x minus 2. So within that simple trinomial, I'm looking for product and sum, two numbers that multiply to -2 and add to -1. The only thing that multiplies to 2 is 1 and 2. So to get the -1, have the -2 be larger and the positive be on the 1. So therefore I have my 6, and then I break that down into x plus 1 and x minus 2. That's my factored form of the derivative. So therefore my x values, or my critical numbers then, would be the opposite, -1, right? I'm just setting x plus 1 equal to 0, right? So then x would equal, bring that over, 0 minus 1, right? And x would be also positive 2. Because again, if x minus 2 was equaling 0, 0 plus 2, bring the -2 over to the other side, and I end up with 2. I just like to go straight to the answers if I know it's opposite the bracket. You might get more difficult ones where you need to do the work and you just set the entire bracket equal to 0, right? So that part is done. Therefore, my critical numbers are, x equaling -1 and 2. And again, put them in numerical order from least to greatest, just like we did in the other video. I'm just looking here. Unfortunately, I think I'm going to need more room than this. So just again, make sure you have this down. I'm going to need to move this up. Classify those critical numbers as local maxima or minimum points, or neither, because we said it's not 100% that they're turning points there. We just know that something important is happening there. It could be that that is an asymptote, and again, we're not there yet, but that's why we have to say or neither. They're not 100% maximum or minimum points. So again, to do that, I need to list them on a number line from least to greatest, figure out what my intervals are, and put that into a chart. So I'm going to, move this up as much as I can. So from my number line, maybe I can even put the number line over here. I had 2 values, right? So I have one value of -1 and one value, critical number, at -2. So then this is my x-axis, right? From -infinity to +infinity. And again, my intervals would be from negative infinity to negative 1, from negative 1 to 2, and from 2 to infinity. So I have 3 intervals here. So I need to know if I'm increasing or decreasing in order to figure out if I have maximum or minimum points. So I've identified my intervals. I have 3 intervals here to work with. Those 3 intervals need to go into the chart. And again, I'll talk about that once we get the chart. I was just going to say, make sure you're choosing numbers that aren't those exact numbers. So I have 3 intervals. I need 3 columns, right? But 1 additional one. So I need 4 columns here. So one of my values is from negative infinity to negative 1. The other one is from negative 1 to negative 2. And then from 2 to infinity. Okay, and then this side here again is going to be my factors of the derivative. Was it f? My factors of f prime of x. So if I go back and look at my factors, so I'm looking at just the bottom of 1a, where it was 0 equals 6, bracket x plus 1, bracket x minus 2. So my factors there were 6, right? X plus 1. Whether it's in brackets or not, it doesn't really matter. X minus 2. Then we have our overall sign for the derivative. And then we have whether it's increasing or decreasing for the original function. Okay. So if I were to pick a number, again, any random number I wanted to between negative infinity and negative 1, but I cannot choose negative 1, right? So let's say I chose negative 2. How do I sub negative 2 into 6? There's no x value there. So whatever the number is, my ending value is going to be 6, which is a positive number, right? Negative 2 plus 1 will give me negative. Negative 2 minus 2 will lead me to negative. So what is a positive multiplied by a negative? A negative. And then that negative multiplied by a negative would give me a positive result overall, right? So that positive result means my original function is increasing in this interval. Now I want to pick a value between negative 1 and negative 2. Oh, is that positive 2? Oh, positive 2. I don't know why I have negative 2 down. Just good thing I noticed and didn't continue. Between negative 1, between negative 1 and 2, because I also have 2 here. Okay, perfect. So between negative 1 and 2, you could pick 1. Whatever, let's say pick 0. 0 is usually easier. Again, 6 is going to be positive all the way through, right? We know that. 0 plus 1 is positive. 0 minus 2 is negative now. So I have positive, positive, negative. So a positive times a positive is a positive. That positive times a negative is now negative. So now I am decreasing throughout this interval. And now a number larger than 2. You could pick decimals if you wanted to, but let's just say we choose a 3. 3 plus 1, 4 is positive. 3 minus 2 is 1. That's still positive. Obviously, multiplying a positive, my answer will be positive, and here I am increasing over this interval of the function. So going back to my question, it says classify the critical numbers as either local maximum or local minimum points, and it also tells us the points, so we would need the y values as well. So if we take a look here, if I'm increasing here, and then I'm decreasing here, then we would know that this is a local max, right? And then if I was decreasing here and then going back and increasing here, this would be my local minimum. So just to put this here, this point here would be my local max. This point, again, here, but we're getting it from this line here, would be my local minimum. So again, where am I here? I'm at x equaling negative 1, right? And here I'm at x equaling 2. So let's write that over to the side here. Therefore, my local max at x equals -1. I have a local max at x equals -1, but in order to get the y value, I go back up to the original function and I type in -1. So that was 2 times -1 cubed minus 3 times -1 squared. Again, you guys can do the work for this. 12 times, sorry, -1 times -12 plus 2. And I'll show you, let's say, the work for this. I'm not going to show you the work for all of them. -2 minus 3 plus 12 plus 2. -5 plus 14 would be 9. So therefore, I have the point -1 and 9 as my local maximum point. And I have a local min at x equals, again, because in between these two, it's hovering around 2. I have the minimum value at x equals -2, but what's the y value there? So I go back to my original and I sub in 2 anytime I see x. Okay, do I need to write that out, right? 2 times 2 cubed minus 3 times 2 squared minus 12 times 2 plus 2, and you're going to end up with, we can pause it, try it, -18. So therefore I have the point of 2 and -18 as my local minimum there. Okay, so now if we look at C, I might need a little bit more room. Find the absolute maximum and minimum, over this interval. So this interval is from x value of -2, including -2, to 4 and including 4. It's a closed interval, right? So this is what we were talking about before. This has endpoints. So it's a closed interval. There's no arrows on the curve. But if I look at my local max and min, my x values only, right? So I have a maximum value at -1. -1 falls within this interval. And I have a minimum value at an x value of 2, and 2 falls within this interval, right? So they both fall within the interval. So let me start by looking at the end points then. So I need to determine the y values of my endpoints. So again, we're subbing it into the original. So we're subbing f at -2, same as here, right? -2 cubed times 2, -2 squared times -3, -2 times -12, and plus 2. And when you sub in -2, actually I get a y value of -2. So this would be the point x -2, y -2. And if I sub in the other endpoint of 4 at an x value of 4 into the original function, I have 34. So therefore I have the point 4 and 34 for my two endpoints, right? So then let me write down, just to kind of write down the information from here within this question. So here are my endpoints, but my local max, just to change the color here, I had a local max at -1 and 9, right? And I had a local min at 2 and -18. So these are my local extrema. They came from the local question for B, right? So what I want to do now is I need to look at all my y values. So if I look at a y value of -2, y value of 34, y value of 9, and y value of -18. Because, just to change the color again, my absolute maximum would be the highest y value. So my absolute max at highest y value, which is 34. So this is my absolute max, absolute maximum point. There isn't another point that is higher than this. And my absolute minimum, same thing, right, is at my lowest y value. Now we're only talking about within this interval, right? So my lowest y value, -18, right? So that means that this point here would be my absolute minimum point along the curve within that interval. Absolute minimum. Okay. One more question. Moving along here, determine any local extrema for g of x. So g of x is x to the power of 4 minus 3x cubed plus 5. So to get local extrema, we're referring to turning points that are probably happening right when the derivative is equal to 0. So when the derivative function is equal to 0 and we have those critical values, they're probably turning points, we're saying, but we can't say 100%. So what we need to do then, if the derivative is equal to 0, is get the derivative. So let's get g prime of x equaling 4x cubed minus 9x squared, and then that would be it, plus 0. And again, this is happening when the derivative would be equal to 0. So we set our derivative, I should have said g of x, sorry, g prime of x, equal to 0. And solve. So we want to find the critical numbers. We need to factor. So there's no number between the 4 and the 9, but I can pick out a common x squared. So that would leave me with 4x minus 9. Now be careful. This isn't squared, so it's not a difference of squares. I can't square root just x, right? So that's as far as I can go. So then my critical numbers then would be x equals 0. What goes in this place by itself to equal 0. And here again, if you weren't sure how to get that, you could just make 4x minus 9 equal to 0. 4x equaling 9, divide by 4, divide by 4. X is going to equal 9 over 4. Or it's just the numerator is the number without the variable divided by the number with the variable and opposite sign, right? It's always opposite sign. So x is 9 over 4. So then we do our number line to make sure we're putting the numbers in numerical order from least to greatest. So 9 divided by 4 is 2.25. So the 0 would come first, and then my 2.25, or if I wanted to leave it as 9 over 4. So how many intervals do I have here? Just looking for it. So I have, sorry, let's go back here. Again, I should label that this is negative infinity, positive infinity. This is my x-axis. So I'm looking at an interval between negative infinity and 0, an interval between 0 and 2.25, and then 2.25 to infinity, right? So I have 3 intervals here again to make my chart. See if I can fit it in here. So the first column is going to be my factors of the derivative. So my factors of g prime of x. And then next would be my first interval between negative infinity and 0. My next interval would be between 0 and 2.25, or you could leave that as a fraction, 9 over 4. And the next interval would be between 2.25 or 9 over 4 and infinity. So now list my factors of g prime of x. So that's right here, my factors of g prime of x. The derivative would be x squared and 4x minus 9. So I only have the 2. Then I have my overall sign for the derivative. And then I have whether I'm increasing finally or decreasing for, I keep wanting to put f, sorry, for the original function g of x. Okay, let's take a look. I don't mind doing the charts. I don't know about you guys, but find them not too bad to do. So again, picking any number you want between negative infinity and 0. So maybe I want to pick, it's totally up to you, negative 1. Negative 1 squared would be positive. 4 times negative 1, right? Negative 4 subtract another 9 would be negative. So positive multiplied by a negative, I'm only doing 2 now, would be negative, and negative would mean that I'm decreasing in that interval. A number between 0 and 2.25. I can't pick 0, right? So 1. 1 squared is positive. That would be 4 minus 9. That would be negative. So then my overall is negative. So this one is decreasing as well. So don't just assume that it's going to be every other, right? You actually have to do the work here. And then a number bigger than 2.25, I could pick 5. I could pick 10. I could pick 2.5. Let's say I pick 3. 3 squared is 9, positive. Here, 4 times 3 is 12. 12 minus 9, I'm actually getting a positive result. So when I multiply those, I get positive. And this section of the curve would be increasing. So again, if I were to look at this, I'm decreasing, decreasing. I get to here and I continue to decrease, decrease, decrease. Then I have nothing happening. At this point here, I have no local max or min happening, if that makes sense. There's no turning point there, right? But here I was decreasing, right? And now I'm increasing. So then this point here would be a local minimum. And that minimum would be happening at 2.25, 9 over 4, right? At 2.25, however you want to write that. So it said determine any local extrema. I could go ahead and get the point then. So let's get the coordinate point now. So all I do is sub in, so therefore this was a local minimum. At x equals 9 over 4, or 2.25, sub that into the original, remember. So g of x is now whatever, 2.25, equaling, again, 2.25 or 9 over 4 to the power of 4 minus 3 times 9 over 4 cubed plus 5. So again, you'd have to take 9 to the power of 4, 4 to the power of 4, 9 to the power of 3, 4 to the power of 3, take that numerator and times it by negative 3, get an LCD. Again, I'll leave you guys to do the work. And I have negative 907 divided by 256. Or if you had put in the value of 2.25 and then put it to the power of 4, 2.25 cube it, and then multiply it by negative 3, you would get the decimal equivalent of that, right? So therefore, my point then, I have a local minimum for all of this chart for these critical numbers. I only have a local minimum occurring at 9 over 4 and negative 907 over 256. And here at 0, I don't have a max or min happening there.